Chapter 5, Lesson 4 is on polygons and their angles. Polygons are simple, closed figures formed by three or more line segments. And I included that closed means that all the sides, all the line segments are connected. An example of a closed shape would be a triangle. A triangle is a polygon, but if I had still three sides, but notice these do not actually connect, this is not a polygon. We also have heard before of equilateral. You've heard of equilateral triangles where all the sides are the same. And as we get further into polygons, we're going to add in there equiangular. Equiangular is when all angles have the same measure. Using the idea of the equilateral triangle I mentioned, we know all the measurements are the same, and we use these marks to say, hey, each segment with that single mark is the same. But we also have that the angles are all 60 degrees. If a shape is both equilateral and equiangular, we're going to call it a regular polygon. A regular polygon is a polygon that is both equilateral and equiangular. So if all the sides are the same and all of the angles are the same, then we have a regular polygon. To start off talking about the angles, we have what's called the interior angle sum of a polygon. We know interior means inside, and what this is looking at is the total of all of the inside angles. So interior, again, is inside. And we're going to look at, if I were to give you the name of a shape, the name of a polygon, you could take the number of sides and place it into the equation we're going to learn and find what that total sum is. And we use that as we move forward. We're going to use it to even figure out, okay, if this is the sum of all the angles, what if I just want to know one or two of those? The equation we're going to use is that S, which is the sum, is equal to n minus 2 times 180. N is the number of sides. Now, I will forewarn that with the work that we'll do, in some cases, they expect that you already know certain terms, such as the names of some of the shapes, but I will try to point out any of them that you might not have seen before. Let's look at an example. Find the sum of the measures of the interior angles of a decagon. Deca is a prefix that means 10. So I am talking about a 10-sided shape. So the in my equation is going to be 10. I use the equation S is equal to n minus 2 times 180. I need to place the 10 where the n is, and then I can begin to solve. Parentheses first, I have 10 minus 2, and that's 8 times 180. Either do this by hand or check in a calculator, and you find that the total sum is 1,440 degrees. I would like to point out that if you look here where I first replaced the n with the 2, I'm sorry, n with the 10, you could have placed that into a calculator as long as it's scientific, and it would have given you the answer. So use technology when it's available, and it can help speed things along if that's what you would like. This table on the right has 4 different shapes. It includes the number of sides, a shape that goes with it. It says number of triangles and sum of angle measures. Now, what that's telling us is that any polygon is made up of a combination of triangles, such as, like we know a square, if I cut it like this, it's 2 triangles. A pentagon can be broken up into 3 triangles. So all polygons are made of 1 or more triangles. And that is where we piece together the equation. 180 we should recognize as the sum of the interior angles of a triangle from the previous lesson. And there happens to be a pattern that going from the number of sides to the number of triangles is just -2. And it's using that pattern to help us come up with the equation. Let's go ahead and we'll use the equation on a few more shapes, and then we're going to look at what if I just want to know one of them. With each of these, we need to start with how many sides there are. A hexagon is a polygon with 6 sides. So I begin to puzzle together my equation. I left a blank where the n goes. I'm going to substitute in a 6 and begin to solve. Parentheses come first. So this is 4 times 180. Giving me 720 degrees. For an octagon is 8 sides. So I'm going to take my equation and instead of n, I'm going to replace it with 8. I'll simplify inside of parentheses first. And I end up with a total sum of 1080 degrees. Every polygon has a name, and that name tells us the number of sides based on of the prefix. So the part that comes before gon tells me the number of sides. After we get past 10 and sometimes 11, the names for them start to get rather long. And so after we get to 10, most of the time you're going to see something similar to 15 gon. The part more important to us than the name is just the number of sides. And what this means is that n is 15. The prefix just tells me how many sides. So it's great when they just give me a number. I'll go ahead and place that into the equation. I'm going to clean that up. I'll go ahead and simplify. The 15 minus 2 is 13 times 180, giving me a total sum of 2,340 degrees. Next, We're going to look at a question on just finding one of those angles. So finding one interior angle. Sometimes, as we're trying to find and piece together these shapes, we might be trying to figure out an angle that is made up of a few different things. So like if I have, say, a square and I put it next to a triangle, sometimes I might be trying to figure out what these angles add up to. So we would need to find what one angle is from the square and one angle is from the triangle. Though we're not using that here, that is an application of this information. This states that each chamber of a bee honeycomb is a regular hexagon. Find the measure of an interior angle. This means one interior angle. With a hexagon, n is equal to 6. Now, the thing that we know is how to find the sum total. If I want to know one interior angle, we could use the sum divided by the number of sides. And that would look like n minus 2 times 180, then divided by n. We don't have to use this whole equation to help us do this. We could do it in pieces, and that's how I'm going to demonstrate. To find one interior angle of a hexagon, we're going to start with finding the sum of those angles. So I'll go ahead and replace n with 6 and solve. Let's see, what was our answer before? Our answer was 720. So that's 720 degrees. But again, that's the sum of all 6. For one interior, I will take the 720 degrees and divide it by the number of sides in. So that is 720 degrees divided by 6, giving me that one interior angle is 120 degrees. So if I want to find one interior angle of a regular hexagon, we need to find the sum and divide it into all its pieces. We also have exterior angles. These are angles that are on the outside of the polygon, and they're made by extending each of the line segments, as you can see in this model here. In a polygon, the sum of the measures of the exterior angles, one at each vertex, such as the model, is 360. So it does not matter what kind of pentagon it is. It doesn't matter that it's even a pentagon. What matters is if it is a polygon, then all of the exterior measurements add together to make 360. We can see that here with this triangle, and they added that already. And then again with this quadrilateral, where they add up to 360. We're going to use this to find one exterior angle. Find the measure of an exterior angle in a regular hexagon. To do this, we're going to look at the total and again divide it by number of sides. But this is not the interior total, it is the exterior total, which is always going to be 360. So to find an exterior angle, we're going to take 360 and divide it by the number of sides. For a hexagon, n equals 6. So we must find what is 360 divided by 6. And I find an answer of 60 degrees. I don't want you to look at this and think, oh no, it can't be that easy. This is all you have to do to find that single exterior angle. We'll go ahead and do 3 more. Again, we need to know the number of sides. For a triangle, n equals 3. So for an interior angle, that's 360 degrees. Divided by 3 to find 120. For a quadrilateral, n equals 4. So for an exterior angle, 360 divided by 4 is going to give me 90 degrees. For an octagon, n is once again 8. So 360 divided by 8 gives me 45 degrees.